Okay, we're still live. Okay, on to the teaching portion of the program. All right, so I do that with the waves because I want to show a resonance with the program is Audacity, by the way, and I want to show a resonance frequency and sound you can hear, and so that way when you see these, it starts making more sense. Yeah, scoot out. All right, so what are the modes? The colors of the spectrograph of the Schumann are plotted from the dependencies of the four modes of amplitude, four modes of quality, and four modes of frequency. And what does this mean? All right, so you have seen the... Okay, I've shown this before. This is common enough on my channel. These are the dependencies. So this is 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are the 12 dependencies of the sub-dependencies of amplitude, quality, and frequency. All right, so when we have the modes, right, and this is something that I need to go into over time, but I wanted to introduce exactly what we're talking about here. And this is a perfect illustration here of the modes on this side here and the modes over on this side here. Yeah, zoom out, make sure we got all this. All right. Sorry about that. All right. So you can see that in this occasion we have the modes are broken up into a various range of frequencies. The high on this is 40, the high on the green one here is 27, but this one starts at 2 and then this one starts at 1. Okay, so when we talk about modes, they're the colors, but what does that really truly mean? All right, so the mode numbers. Okay, so a mode of vibration is characterized by a modal frequency and a modal shape. It is numbered according to the number of half waves in the vibration. For example, if a vibrating beam with both ends pinned displays a mode shape of half of a sine wave, one peak on the vibrating beam, it would be vibrating in mode 1. If it had a full sine wave, one peak and one trough, it would be vibrating in mode 2. Okay. Now, what it's showing you, we're talking about here, is this. Okay. So, these are the modes of the magnetic spectrum, but when it's talking about a standing wave, all right, these are the modes. That's what he's talking about here. All right. So vibrating mode 1, mode 2, mode 3, and mode 4. In our case, we have 4 modes. In a system with one or more dimensions, such as in the picture disk, this right here, okay, and there's also a GIF, a moving GIF that goes with it. Okay. Each dimension is given a mode number. Using polar coordinates, we have a radial coordinate and then an angular coordinate. If one measured from the center outward along the radial coordinate, one would encounter a full wave, so the mode number in the radial direction is 2. And the other direction is trickier, only because half of the disk is considered due to the anti-symmetric, also called skew-symmetry, nature of a disk's vibration in the angular direction. Thusly, measuring 180 degrees along the angular direction, you would encounter a half a wave, so the mode number is in the angular direction is 1. So the mode number of the system is 2 to 1 or 1 to 2, depending on which coordinate is considered the first and which is considered the second coordinate. So it is important to always indicate which mode number matches with each coordinate direction. In linear systems, each mode is entirely independent of all other modes. In general, all modes have different frequencies, with lower modes having lower frequencies and different mode shapes. Okay, all right. Now, I wanted to show this, and that is not that. Okay, let me pull up my browser here. That is not that what I wanted you to see. Hello. All right, that is not that. There it is. I'll have to fix the emails and edit. Okay, so I'm going to shift the camera so you can see this. This is essentially what our electromagnetic waves are doing. They're going from amplitude into the height is the amplitude, the magnetics is the width. Okay. Now, back to our teaching material here. Modes. Okay. So, our standing wave diagram is this right here. Okay. Now this is one of the more important things to understand about the modes of the Schumann harmonics resonance. Okay. Where we are at with this is matching up the color with the frequency, the wavelength. This is amplitude. Okay. It's showing you what a standing wave is, but this is the amplitude of our signal, which is, zoom out, the amplitude of our signal is right here. Okay, so our amplitude of our signal is right here in this section here. All right. So we look here, the green happens to match up with our green there, the red happens to match up with our red there. Blue is the blue of the background of the spectrograph, which we're going to get into later. The T1 yellow is actually white here. So it's really close, what they're doing here is really close to the colorations of what it actually is. Okay, by chance or by grand design, either way it doesn't matter. So when we're looking at our modes, okay, modes of amplitude are shown by way of analogy. T1 is our white mode here, and then the blue is our yellow mode there. 3 is our red mode here. 4 is our green mode here. And you notice something interesting, that it's doing one of these things that we just showed. It's flexing, okay? There's this flex going on with this dealio here, okay? And this is in an in an oscillating system, okay? Is a repetitive variation, typically in time of some measure about a center value or between two or more different states. The term vibration is precisely used to describe mechanical oscillation. Familiar examples of oscillation include a swinging pendulum and an alternating current. All right. Now, we don't get into mechanical oscillation until it becomes the magnetic portion. This right here is the amplitude, transferring it to magnetic, and that is the magnetic portion where it goes into oscillation. It's a measure precisely used to describe mechanical oscillation. So the electric portion is not the mechanical, even though there is a physical thing. That is like a strike of the gong, if you will. It is not until it actuates into mechanical, the quality energy, It's not until it actuates into quality, this part here, that where it is a mechanical transfer of the energy. Okay. So in physics, a standing wave is also known as a stationary wave. All right. So right here, this diagram and this diagram are over on Wikipedia. I'm going to go over there right now. Essentially, this is the harmonics on a string. This is the quality portion of that, the magnetics, the heavier latitudinal, I guess. These are latitudinal waves. These are longitudinal, okay, as it were. The electrics are 90 degrees vertical. The horizontal, the magnetics, rather, are the horizontal in a V shape, if you will. All right. So we're talking about normal mode. All right. So these are the modes. This is an explanation, still an explanation of what the modes are, but you got to understand how they are scientifically, actually, technically created before you can understand really, truly what those colors on the graph mean. All right. So it says a normal mode of an oscillating system, here it is a pattern of motion in which all parts of the system move sinusoidally. Okay. Sorry. Okay. A sine wave is a sinusoidal or mathematical curve that describes a smooth periodic isolation. A sine wave is a continuous wave. It is named after the function wave of which it is the graph. It occurs only in pure and applied mathematics, as well as physics, engineering, signal processing, and more, blah, blah, blah. All right. With the same frequency and with a fixed phase relation. The free motion described by the normal modes takes place at fixed frequencies. Okay. These fixed frequencies in the normal modes of a system are known as its natural frequencies or its resonant frequencies. Okay? Right there. Now, this right here, resonance, is what is happening with the Schumann resonance spectrograph. Okay? Before I go into the bit about Ezekiel's wheel, which was originally the next one in the series, my guides told me to talk about the modes and to talk about this first before going into the more advanced stuff of why and how one would be seeing the hexagonal shape or some shape like that. It's not random, it's not happenstance, it actually is due to the mathematical curve here, which is actually not just mathematical, like this is an actual thing. You see it on the Schumann resonance, but what does that mean? Wage's World had pointed out the hexagonal shape of Ezekiel's wheel he's talking about, and this is the wheel. This is that wheel of Ezekiel's wheel in there. You have the amplitude spikes going that way. You have the horizontal wave of that, right? Move this over so we can see it. Can we see it? Right? All right, good. Yeah. Right. So you can see what it's doing. Bang, bang. And then it sends out these. There's a spike in amplitude. There's a white spike. There's a white out right there. See, it's almost showing you. White out, bam, right there. And then when it goes down, that's going into the ground. Yet, it's not. It's just coming back somewhere there. See, the magnetics are going to be hugging around the Earth, around the planet. You see that it's there, how tall that was. The return of this is not very big relative to the amplitude spike that had come in. All right. So when we're looking at this, we see the modes. So we're looking at this, we see the modes. This would be our first amplitude, this one here. That's our second, or that's mode 1. Actually, technically mode 1 is here, ends here. But this, for a practical purpose, this is mode 1, amplitude 1. This is amplitude 2, that's amplitude 3, and that's amplitude 4. Or maybe that is amplitude 4, I don't know, probably that would be 4, keeping in line. All right, so that's, and then, as necessary, that would be an amplitude 5. If we had a 5, it would be down there, measuring the lowest of the lowest of the low. Okay, and so we see here, on the amplitude strike coming up, this is a quality. This is our quality modes here, sorry. So this would be quality, which way are we going from? Quality, I would think that that's quality 1, quality 2, quality 3, quality 4. I would believe, I'm not quite absolutely sure, but that would be our quality on that side. This is our amplitude mode, that's our quality mode on that side. Or quality dependency with the 4 modes there. I think that's anyway. Right, so it says, earthquake test, right? So it says, resonance describes the phenomena of increased amplitude that occurs when the frequency of a periodically applied force is equal or close to the natural frequency of the system on which it acts. When an oscillating force is applied at the resonant frequency of a dynamical system, the system will oscillate in resonance with the... Okay. When an oscillating force is applied at a resonant frequency of a dynamical system, hello. The component is resonant. Where am I? Oh, resonance describes the phenomena of increased amplitude, right there, that occurs when the frequency of a periodically applied force, or a Fourier component of it, is equal or close to a natural frequency of the system on which it acts. When an oscillating force is applied at a resonant frequency of the dynamical system, the system will oscillate at a higher amplitude than when the same force is applied at other non-resonant frequencies. All right, I'm not going to go into explaining too much of what that is because it's actually a little beyond me, and I'm almost at the end of the video. All right. So that's part of what I want to show. Let's go back to normal mode. All right, so that was the picture disk, and I'm really just going over what was in the graphic that I had made, the teaching instructional. This is just really a warm-up on the topic of what the modes actually are. So this isn't so much the teaching lesson right now, just so much as it is a kind of one-on-one description of what I was pointing out in the graphic that I made, the teaching description. All right, so this is a standing wave, and I wanted to show you this really cool thing. All right. All right, so this really cool diagram is, in physics, a standing wave, also known as a stationary wave, is a wave which oscillates in time, but whose peak amplitude profile does not move in space. Okay, it's important to know that. See that these guys here are staying fairly fluctuated or fixated, I guess, in space. They don't move. The resonances don't move. The standing waves don't move. They stack up. You can see them kind of starting to stack up there. Okay. Does not move in space. The peak amplitude of the wave oscillations at any point in space is constant with time, and the oscillations at different points throughout the wave are I'm not going to go into that. Let's open a link. All right. I see they show the nice diagram over there. All right. The oscillations at different points throughout the waves are in phase. The locations at which the absolute value of the amplitude is minimum is called nodes. And the locations where the absolute value of the amplitude is maximum are called antinodes. Okay. All right. So those are the... Okay, so this is my standing wave. This is the fundamentals of the first overtones of the vibrating, which you can't see. You really cannot see that over there. All right, so this right here is the fundamental of the first 6 overtones. These are the harmonics of a string. Okay, and I'll be going into this in future videos. These are your standing waves. Okay. All right, and so this is an interesting graphic. So it says a mode shape of a drum membrane with nodal lines shown in pale green. All right, so I want to zoom in. So these are mode shape of a drum membrane with nodal lines shown in pale green. Now, picture your ear, tympanic membrane in your ear being such. I think that's really important to mention that, okay? So when we're talking about a one-dimensional system, at a given mode, the vibration will have nodes, or places where the displacement is always 0. These nodes correspond to points in the mode shape where the mode shape is 0. Since the vibration of a system is given by the mode shape multiplied by a time function, the displacement of the node point remains 0 at all times. I'm not sure what I just read there, but I am giving you a kind of heads up that problems ringing in your ears has a lot to do with the non-medical related ringing in the ears may have a lot to do with the electromagnetics coming in at this time. Okay, so I'm going to this is a current shot of the Schumann harmonics resonance, or Schumann resonance harmonics. That's that. Right, so this is the full capture report, and you see the modes. Ding, 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 ding. Okay, we had a spike. This is 42. Here, that was probably, I would imagine, that some of the stuff coming off of the sun from the 17th, like the very tail end of it, because all this counts too. This is during the day. This is 6, 7, 8, 9, 10, 11, 12. This is the afternoon right here. This came in the afternoon. I'm going by the this is their local time. The little number on the bottom is their local time. Okay. All right, so whenever I'm looking at the Schumann report, the spectrograph, I need to see the dependencies that come with it. And as I explain, as you go on further and you understand what the dependencies are, how important they are to being able to tell what's going on with the Schumann, you'll understand more of what you're looking at here. Once you know what you're looking at down here, the modes, what these modes are, you'll be able to determine what is a true resonance and what is something else happening that may be local to the observatory, or it may be on a worldwide scale. But without knowing what is what, you will never know which it is, whether it's local or whether it's something that's happening around the world. And if you're keeping track of things, it's important to know that. All right. So, with that cheery news, thank you. This is a latest shot of the Schumann that I'm going to go out on. All right. So, we're at 26 over 25 minutes, or getting in 30 minutes. Thank you very much. This is Verdi Arbusto making a video for the Schumann Resonance Harmonics channel, and I thank you all for being here, and I appreciate your coming and saying hi. So, namaste, and have a great rest of your day. Much love to all of you, and I appreciate you being here with me. Thank you.